تمام سامعك. اوكي. Assalamu alaikum wa rahmatullahi wa barakatuh. Good evening, everyone. Thanks for joining this event, and I would like to thank you for being with us tonight. And also, at the same time, I would like to thank the organizers for that event. Before we start, let me introduce myself. My name is Hany Beeh. Currently, I am working for Schlumberger DNM Norway as a drilling engineer for the last 5 years. Before that, I used to be a DD, or direction drilling engineer, working for Baker for almost 5 years, and my first job was a production engineer. Today's topic is basically understanding torque and drag models, and today we'll cover this topic in a practical way. So the idea is to transfer the experience and the challenges we have had when we design drill string. The agenda for today will go through mainly two parts. The first part contains an introduction, so we go through torque and drag, what is torque, what's drag, what is drag, and at the same time, what are the causes of torque and drag, and then we'll elaborate and talk a lot about the main contributors or the main causes for torque and drag, which are the side forces and the friction. On the second part, we'll cover mainly the models or the simulations. We'll discuss about the inputs, what are the main inputs and how the inputs can affect outputs, and then we'll cover the outputs and see that with some few examples. We'll not cover the whole outputs that we can get from torque and drag simulations, but basically the plan is to cover the most important ones and the main contributors or the main factors that can change the whole picture. Okay, first let's ask a question. Why do we need to perform torque and drag? The thing is, basically, when do we design a well? It depends on where you are and what kind of experience or what kind of things that you have in your mind before you design a well. Like it depends on your team. So some people actually believe that they have a certain drill pipe, so they have the drill pipe available, and they can go and drill the well without even thinking about doing any engineering. It's a gut feeling. They think it will work, but does it work all the time? I don't think so. Some people have a lot of experience, which is really good, and at the same time, they think this experience might help them, so they have been using this setup of drill string, and they believe that they can use it for every single well. Yeah, so experience is really important, but at the same time, they don't take into account the changes or that if there is only one thing in the inputs has changed, that might change the whole picture. So they have to think about different things. What if they have a different rig capacity now? So they have changed the rig and they have a smaller rig with smaller capacity. Will the design or the drill string design fit in this rig capacity? So that's something they have to think about. What if they have new drill pipes with new specs? So that's another thing they have to think about. Another thing, what if they have changed the well design? So they used to drill, let's say, vertical easy wells, and now they are drilling ERD wells. Is it the same thing that you can use for both of them? Can you use the same setup you use for vertical well into ERD well? No, it's not for sure. And then what if you have new profile or new design for casing? It's another different thing. So yes, experience will help, but sometimes it's not relevant. So you have to make sure that you do it in the proper way. And this proper way is basically the engineering design. So you have to, for each single well, we have to do an engineering design. We have to do hydraulic simulations to make sure that this string will fit and it will be within the rig specifications, within the rig pump specifications, so you will not exceed the standby pressure. You have to do torque and drag simulation, so you don't exceed the limits in your drill pipe, and at the same time, you know you're within your technical limits for the rig. So that's the way we should usually or always do our design. And why that? The main reason for that, it's the need for engineering design these days has become a necessity, because for the recent few years, the wells are becoming more complex. So early days was easy to drill a well and get the oil, but now it's much more complex to drill and get and hit the targets. So you have to drill ERD wells or TTRD wells. So and also you have to do like HPHT, deep water. So everything is getting more complex now, and accessing the targets or getting into the targets requires much more accurate drill string design. And based on that, the cost of the wells also has increased a lot. So imagine yourself drilling a well that may cost $20 million or $30 million, and you don't have any engineering basis or any engineering design. Again, the same question. Why do we need to run torque and drag? We need to make sure, the reason we do torque and drag simulation, which is part of drill string design, we need to make sure that with the current setup we have in the design, we can reach the LTD. That's the whole idea, because we aim to hit the target and case the well and make it produce. So imagine if we drill a well and at some point we just discover that we can't get into the target. It's a shame for sure. Then the second thing also, we need to make sure that our design can fit within the rig limits. So you have the technical limits for your rig. You need to know the hoisting system limits. You need to know the standby pressure or the pumps limit. You need to know the top drive torque and RPM limits. So you have to make sure that your design fits in these limits. Otherwise, you'll be in a trouble. Then one other thing. The most important thing as well is that you need to utilize the drill pipes or drill string you have for different sections. So you can't really use one drill pipe for the whole well. So you can't drill a 6-inch section or 8.5-inch section with 658 drill pipe. So you have to use smaller drill pipe, and then you can use 658 in bigger sections. And at some point, probably in 12-1/4, you may need to use 658 with 5-inch as a tapered string. And the reason for that, because you have to optimize your drill string for different things. So you have to optimize your drill string for torque, for drag, for hydraulics, which is standby pressure, ECD. So you have to make sure that your drill string fits all the purposes that you need. Okay, so after this introduction, let's go about the main contributor or the main causes for torque and drag. So basically, first thing, the definition of torque and drag. What is torque and what is drag? Drag is basically an axial force. So it's a one-dimensional force, and this is generated due to the interaction or the contact force between your drill string when it's moving and the formation and or the casing. So basically, when you move in an axial way, you generate a force, and this force is the drag. And it's usually in the opposite direction of the movement. Then your torque is basically, it's the same concept, but at that time you are rotating, because you need to drill, so you need to rotate your string to be able to drill. And when you start rotation, then you actually generate a contact force again between your drill string and the formation. But this type of force in that way is a rotational force. So as we said, the causes of torque and drag, there are two main causes of torque and drag, and these are the side forces. And if you remember the definition we just said, the torque and drag are actually the interaction between drill string or the contact forces between the drill string and the formation. So that's a main contributor to the torque and drag. So it's a side forces that is generated due to this interaction. And the second thing is the friction from the formation or the drill string when you move, or the casing, when you move the drill string along it. So that's basically due to the movement of drill string and in the formation and in the casing. So these are the two main.
Share screen.
Excuse me, I can't hear you.
Share your screen.
Okay. Okay. Yeah. All right. Yeah. So as we said, there are two main causes or contributors for torque and drag, which are the side forces, the interaction between the drill string and the formation and the casing. And the other one is the friction. So there might be some other causes for torque and drag, but usually this happens when you have a problem. And these causes could be the hole cleaning. If you have hole cleaning problem in the low side of your hole, then what happens is basically you get more drag and you have higher torque. So, but this is something we don't really need. Wellbore stability, it's the same concept, because basically wellbore stability is that the formation, your formation, when you drill into a weak formation, it can't be held in place. And what happens, it actually falls apart and it causes another, again, a hole cleaning problem. And the same thing in under gauge hole. So basically, that might cause an increase in torque and drag, but these are not the main contributor. These actually are problems that you don't really want to have when you drill a well. So let's talk now about the two main contributors in detail. So we'll discuss the side forces and the friction in details. So there are few components that can actually cause the side forces, and these components could be the weight itself, the weight of the drill string itself, which acts usually to the low side, to the gravity, and also the tension and the drill string. And you never see any effect of tension, or the tension can't be a contributor to side forces unless you have a dogleg. So if you are in tangent, then you shouldn't see any effect of tension. Usually the tangent, the side forces in the tangent will be generated by the weight of the drill string. So when you have a tension and dogleg, then yes, you can see the side forces, and we'll go through that soon. Buckling itself, so when you have your string get buckled, then you have more contact area between the drill string and the formation, and there you can get some side forces. Stiffness of the string, this is the lowest contributor, and I think if it happens, it will be, I haven't expected that to be happening, to be honest, but basically the condition for this contributor to happen is that you need to have too high dogleg, which is 15 degrees per 100 feet. And I think if you get this too high dogleg, then you will get stuck anyway. So the main two contributors here for the side forces are basically the weight of the string, which usually acts in the tangent sections, and the tension with the dogleg. So we'll discuss these in details soon. Yeah. So as we said, side forces contributors are weight component. And if you look at this graph here, so assuming this green box, this object is your drill string, and that part here on the low side is basically your well bore, and you're moving the drill string along the well bore. So what happens, you have the weight component, you have the weight of the drill string pointing usually to the gravity, but then this weight, due to the interaction of the weight of the string, or the string with the well bore, what happens here, you create a side force, which is a weight component of the side force. So that's how we get side forces, by the weight. So the main message here is that when you design a well and you see too high side forces, then you have to think about the drill pipe you're using. Are you using 658, which is too heavy? Can you use 578? Can you go down to 5.5 to reduce this high side forces or not? Because as I said, high side forces means that you increase your torque and drag. And if you have a big capacity rig, and the torque and drag is within the limits, then it's okay. But if you have very limited rig, then you really have to think about these minor things. Then the second component of side forces is actually tension with dogleg. So as we just said, usually you have the effect of tension when you have a dogleg. So if you see this graph here, it shows actually a build section. So we're building an angle, we're kicking off, for example, and we're building an angle. So you see the drill string is a little bit twisted, and that's the well bore. And we are assuming two scenarios here. We are assuming that we're moving down in the first one to the left. We're assuming that we are moving down with the drill string. So what happens when you push the string down? the drill string will be on the low side of your well bore. And hence, the effect of tension would be basically very low, and it will be mostly the effect of weight acting on the low side. So the tension will be too low, and the resultant side forces will be on the low side in that case. Let's assume the opposite now. We're pulling the string, so we're actually trimming out from the hole, and then you have all the tension, you're pulling the string, and then you have maximum tensile strength at that point, and your string will be in contact with the top of the well bore by physics. So it will go to the high side of the well bore. And what happens here? You have the max tensile strength affecting on your high side of the well bore, and then you have the resultant side forces actually in the same direction as the tensile or the tension in the string, or tension component in the string. So as we said, like, this is not the tension itself, but it's a component of tension. So it's just you have the tensile string is along the string itself, the tension of a tensile load. But again, this is the effect of the tension or the tensile on the well bore walls. So that's a tension component in build section. So let's go and see how it look like in a drop section. So in drop section, what happens here is that in all cases, regardless if you're pulling out or running in hole, what happens? Your drill string is always on the low side, so it will be always on the low side. And in all cases, the effect of your side forces will be on the low side, because the tension component of side forces and the weight component of side forces will be acting in the low side. So the resultant side forces will be actually acting on the low side. So the whole idea is, what are the main contributor or the main factors that affect the tension component of the side forces? So if you look at the equation here for the side forces generated by tension, you see that it's mainly generated by dogleg and tension or tensile load on the drill string. So these are the two major components. As you can see, that if you increase the tension on the drill string, if you increase the tensile load, and if you increase the doglegs, then the side forces will be increased. So again, let's think about your drill string back, and assume you have full string with 658 drill pipes. It will be much heavier than the full string with 5-inch. So can you use 5-inch and then you reduce the side forces? Another thing, the dogleg severity. In that case, if you're a DD and you're doing a kickoff at, let's say, 300 meters, I think the main intention would be just to kick off. You need to get high dogleg to get away to build the angle, and then you make your kickoff, and then you're happy. That's mostly how we used to look at it when we used to work offshore. But when you do more engineering and you see what's happening, you look at the big picture now, and you see, okay, if I kick off with, let's say, 4 degrees dogleg at 300 meters, how much that would affect my side forces? It's a lot. If you compare that to 2 degrees dogleg instead, and if you redesign your well with 2 degrees dogleg, then you see the differences on side forces. And as we said earlier, what happens if you have high side forces is basically you get in trouble. So you increase your drag, increase your torque, and then it's a matter of, will you be able to reach your TD? Will you be able to run the casing through it? And if you have, even if you run the casing through it, and then you drill the next section, and you have high side forces still at 300 meters where you kicked off. So what happens there? Your string is rotating, and then you have high side forces on the casing. So the drill pipe is actually subjecting high load on the casing with high RPM and with time. What happens that you get casing wear and drill pipe wear. So you may put your well at risk. So you may actually erode your casing and create a hole in your casing, and that would be an integrity problem. That's why it's quite important to look at these minor details to understand the idea behind it. It's not just to put the string you have or user experience, but then you need actually to look at these minor details to understand how that would affect your final delivery. And that's the big picture that we usually should look at, not just performing your own job as, let's say, as a DD, and we need to kick off. Yeah, the recommendation for the site forces is basically, usually it's like it's measured on the drill pipe length. So it's 30 feet every 30 feet or every 10 meters. So it's 1 ton every 10 meter, and or even 2 kilopound every 30 feet, based on your units. So that's usually the recommendation we look at in our design. So we see that if we're exceeding, sometimes you may exceed by a small margin, but sometimes when it's too much, like it's 3 or 4, then we have to raise a concern, and then afterwards we have to do casing wear simulations to make sure that how much can we wear the casing, and would it survive until the end of the well or not. Moving on to the third component of site forces, which is buckling. As I said, the weight component, tension component are the 2 main components for site forces. Buckling can play a role, but that doesn't usually happen. It happens. We can't really deny that it happens, but it happens sometimes, but it's not a major contributor. So for buckling to happen, it has to happen when the string is under compression. So if you're drilling, let's say, vertical well, shallow depth, and you're applying 30 ton or something, then what happens, your string will be like that. And that's why we call it sinusoidal buckling. So you see that initially your string was straight forward, it was just in the middle, so we had less contact forces. But now when your string buckles like this, then you have more contact forces, and that actually creates more torque and more drag. And then if you increase the weight on bit even further, what happens? So you move from sinusoidal buckling into helical buckling, and then there is a risk that you may part your string, so you may lose your string. Yeah, sometimes you just believe it's a theory and it doesn't happen, but believe me, it happens. So as I just said, so if you look closer to these pictures, what you would see here is basically, look at that drill pipe. Can you see anything wrong? If you look at that, the pictures I showed to you, and relate that to this pipe that in next slide, you will see it's sinusoidal. You will see the sinusoidal buckling. So you can see it clearly here. So the drill pipe has buckled already. Again, same here, that drill pipe. So you can see the bend here in the drill pipe. It's caused by buckling. And that one here. So that's a sinusoidal buckling. But if you look also at that drill pipe there, not sure if you can see it yet, but if you look at it, it's very similar to helical buckling. So that was helically buckled. So you can see it clearly in the picture. So these are true pipes that were buckled already. So it happens. Then again, the question is, how important is it to do your design, accurate design, and make sure your drill string will fit the purpose? That's really critical now. And the last factor, or the last component of site forces, as we said, it's stiffness. And to make this to happen, so basically it depends on, you have 2 high dog leg, and then you have very stiff string here. And what happens is that you create site forces due to the stiffness of that string. And I don't think this happens, as I said, like, because if you have 15 degrees dog leg, then what would happen is that you may actually get key seating first, or your string will get stuck anyway. So this is very rare to happen. It may happen if you have, let's say, if you have casing string and you're running in too high dog leg, which it might be for the casing, it might be 8 or 9 degrees dog leg. And again, it depends on the stiffness of the string you're running. Yeah, so just to recap, as we said, we have 2 components of that can cause torque and drag, which are site forces and friction. We just finished the site forces. And as we said, the site forces components are weight component, which usually happens in tangent sections, and it usually affects the low side of the well bore. And then it's a matter of what is the weight of your drill pipe. That's what you need to look at. Again, the tension and dogleg component, and basically it happens in the build up or drop sections. So whenever you have a dogleg, then and you're pulling out a hole or tripping out a hole, running in a hole, then you see the effect of your dogleg and tension on the string. And the increase of the dogleg actually increases this component a lot. So any increase of dogleg will increase your tension side forces a lot. So you have to consider that in your planning, and it's really important to start your well path design or trajectory design with very low ROP at the beginning, and then increase that gradually as you go deeper. And the reason for that, if you have too high ROP at the beginning, then you still have, at that point, the tension is, or if you look back to the side forces equation, what happens that you have the dogleg, which is there, like let's say 3 degrees right there, and then you have the tensile load, and the tensile load in that case would be the whole weight of the drill string underneath. So if you're too shallow, then you have longer drill string, and then you have too high tensile load. But if you can push this high dogleg deeper, then you actually have much less drill string, and then you can have much less tensile load, and then at the same time you have much less side forces. Then the third component, as we said, buckling. And it happens when the string is under compression. And as we said, we have 2 types of buckling, which is sinusoidal buckling and helical buckling. And the stiffness, it rarely happens. So let's jump now to the second cause of the torque and drag. And this cause is basically the friction. So in general, we won't go through the theory that much, but we'll just give a brief about it. So in general, what is friction? So basically you have an object here, and you're trying to move this object to that direction, and this object has a weight of W. What happens when you try to move the object is basically you have a friction due to the contact or the interaction between the object weight and the surface you're moving on. And then the friction works actually in the other direction. Let's think about this in our case in the well. So you assume you have a well bore like this and has an inclination of theta, and the drill string you have has a weight of W. So when you are static here, when you don't have any movement, basically you don't have any friction. So the friction is 0. And this happens in reality when you try to think about how do we do that in real life. In reality, when you are rotating off bottom, so you're rotating the string, there is no friction because you're not moving in your up or down, and there is no so basically there is no friction generated when you rotate off bottom. And this is really important for us later on. I'll go through it later on. And then the second example is actually you're tripping in hole. So you're running in hole. What happens if you have a friction on the other side? So you have a friction working on against you in the other side. And then tripping out hole, the same thing. You have a friction going down in hole, and that adds weight to you. So you trip with the weight, drill weight. So basically here you have the drill pipe weight when you're rotating. You have the string weight, the point weight of the string when you're rotating here in the first case, because there is no friction. But then when you trip in, what can you expect? Basically, your weight getting lighter because friction is working on the other side, so you have to subtract the friction. And then let's say you have 200 ton of string weight. When you go in, when you trip in, then you should expect like 140 ton or something. So this is normal. So it's easy to trip in that case because you don't need extra weight. But what happens if you trip out with the 200 ton weight, string weight? Then your friction is working against you, and you have to pull extra load from the friction. So if you're 200 ton string weight already and you have a friction of 60 ton, then it's 260. And that might be close to the drill pipe limit or the rig limit. So you have to consider that in your design. So the friction value or the amount of friction you may expect in the well bore is really critical and important. And that's why it's quite important to focus on it. Okay. Let's now talk about the friction factors. What kind of factors that you can expect, or the friction you can expect in hole, and what types of frictions you should think of. So basically, it depends on your motion. If you're rotating the drill string and drilling, like you're rotating and moving the string, then you should expect something called, or you should think about something called rotation friction factor. And basically, it's a friction between the wheel bore and the drill string when you rotate the string. And this factor is quite important, as we said, to how to estimate, because that would affect your final torque output. And then the second type of friction is translation friction factor or axial friction factor. And this happens when you move your string up or down. So if you trip in, trip out, if you're sliding, so this is what we call axial friction factors. So you have to think about your scenario. What are you doing? If you are drilling, then you have to think about rotation friction factor. If you are tripping, then you have to think about translation friction factor, because this is axial movement. You don't have any rotation, so it doesn't really affect. But there is a special scenario, which is back reaming. So back reaming, you're doing both. So if you're reaming up, what are you doing here is basically you're rotating. So you have most of your friction from rotation. So you still have the rotation friction factor. At the same time, you still have the translation, because you're moving in axial direction, or up and down. So it's quite important as well to understand which friction factor you should use for each scenario. And as we just said previously in last slide, these friction factors will affect your outputs completely. So if you have wrong inputs for friction factors, then you shouldn't expect accurate designs. So if it's that important, if the friction factor is that important, how can we get accurate friction factors? What is the source for friction factors? Can we just put any number? Can we just think about, like, okay, I think it can be 0.3, 0.4, 0.2? What kind of the value that you should use in that case? Okay, let's think about it in a different way. So assume you just drilled a well in the same field, your last well, and you managed to get some hook load measurement. So what you have here, you have in the middle, in the black line here, is basically the rotary weight or the string weight. And as we said, like, the rotary weight or the string weight is zero friction weight. So you don't have any friction here. So it's basically just a weight of the string in the mud with buoyancy factor. And then assume, if you look at the weight on hook here, so this weight is higher, and then we should assume this is the up weight. So you're pulling the string up, so you make a connection, you drill, you make a connection, and then you take up weights to check your string. Is it free or not? You take the up weight, and then you go down and you take the down weights when you go in. So just to make sure you don't have any obstruction, or you don't get stuck. So you need to take these weights. Usually it's taken every connection before you do the next connection. So you take rotary weight, up weight, and down weight. So it's an important information, but does it bring any value with the way it is presented like now? Can you get any feeling, like, by looking at this graph? Do you think it's important? Does it bring any value? Can you think about anything when you look at these plots? I don't think so. So let's try to do something different. What can we do in the planning phase? So we have something called prom stick plot. So what is prom stick plot? It's like prom stick. What we do is we simulate up weights in red here and down weights in blue to the left at different depth. And then you have the weights here. So we simulate the up weights, down weights, and then you have simulate the rotary weight in the middle. And we simulate these weights at different friction factors. So we simulate up weights going from in to out at 0.2, 0.3 friction factor, 0.4 friction factor, and then 0.5 friction factor, for example. And then we do the same for down weights, 0.2 friction factors, 0.3 friction factors, 0.4, and 0.5. So how can we use these plots, or what do we use it for? So if you think back again about these weights that we had from the previous ones, if we can do these simulations for the previous well with the same well path, same casing design, and same mud properties, if we use the same inputs from previous well and create this plot and make it, merge it or project the actual weight we had right here. So we project the actual weights we had from the previous well to the roadmaps we created. Does it bring any value now? Can you see the difference now? Now you can tell, yes, that's 0.2 friction factor up weight. What happens here? We have the weights mostly aligned to the 0.2 friction factor. And it's the same for the down weights. So we still have the weights aligned for 0.2 friction factors. So that means we have 0.2 friction factor or translation friction factors, because this is up and down weights. So it's quite important. Now you see the value of having these weights and having the Bromsteg plot. So now when you do a design for next well, you know which friction factors you can use for that section. This is actually 8.5-inch section. So you have to use this for each section. And it's different from one section to another because you have different formation. You have different BHA design, you have different inclination azimuths from one section to another. So these simulations takes into account all these inputs. So let's zoom in here. You see that's exactly 8.5. So you see 0.2 friction factor, 0.2 friction factor up weights. And then most importantly, to make sure that your simulation is correct, is to make sure that actual rotating weight is actually lying on the simulated rotating weight, because this is a 0 friction weight. So it has to be correct. So you can make sure that the weight you have entered for the drill pipe is correct. So now we can get the information from offset wells, and we get the value of the weights we had. Same thing for torque. So if you look at the same thing for the torque, so we have the measurement here from the previous well. We have the off-bottom torque in blue, and we have the on-bottom torque in red. And just for your information, the difference between the off-bottom and on-bottom torque are basically the bit torque. So you can also get the information of the bit torque, how aggressive your bit is. So you can know what kind of aggressiveness you have in your bit. So you know in one of your inputs for your simulation, in torque and drag simulation, is basically need the bit torque. So you can actually get this information from here, the difference between on-bottom torque and off-bottom torque. And then you have the RPM that was used for drilling. And this measurement is taken every connection, as we said. It's same like up weight and down weights. So again, looking at these data like this, it doesn't bring any value. But if we do the same thing, if we project it to the simulated friction factors that we had, 0.2 friction factor, 0.3, 0.4, 0.5, then you see that it's mostly around 0.2. So it doesn't have to be spot on, but it's just close enough to this friction, and it has to follow the trend. That's the most important thing. So we know that we have 0.2 friction factor by looking at that. So just to recap, friction factors, as we said, like we have two types of friction factors. We have rotation friction factors, and we have translation friction factor, which is axial. Rotation friction factor when you're drilling, when you're rotating off bottom, reaming in, or back reaming. And translation friction factor when you tripping in, trip out, slide for motor. And also you can use a very small portion of a translation friction factor in back reaming. So as we said, like friction factors are really critical and important to get accurate outputs if you're really keen to get accurate outputs. And offset data is really important or the only source for getting these friction factors. So you can guess, but again, it won't be accurate. So you have to make sure that you use the right friction factors to make sure that your simulation are accurate. Okay, so now I'm done with my first part of the presentation, and I think we can take the questions if you have any before we move on. Okay, so I see only one question now. How to avoid buckling effect? Yeah, so I would prefer to cover this in the second part, because basically we'll focus on buckling and what are the factors that affect buckling. But in summary, it's a BHA design, well path design, and your parameters. But we'll discuss that in the second session because it will have more details about it. Yeah. Do you have any other questions? Okay, then we'll move on. Second part is basically about torque and drag models inputs and outputs. So we'll discuss in this part the inputs we have to have, and as we said, it has to be accurate to get the right output. It's usually we say like GIGO. It's a garbage in, garbage out. So if you have wrong inputs, then you get wrong outputs. So that's really important. And again, the software is actually does what you. So you feed him in with wrong data, so you feed you or give you wrong outputs. So it's you who can decide how accurate your simulation should be. And then we'll move to the outputs. We'll discuss the main outputs, but I'll focus on a few of them. And then we'll have a few examples on the parameters that can affect your outputs with some different examples and changing the parameters. And then we'll end the session. So yeah, let's move on, and then the inputs that you should have for your torque and drag simulation. Basically, it's wheel bore geometry, which is the casing design. You need to know what depth you drill, what is your open hole, what is your casing, because you may have different friction factors for open hole and different friction factors for casing. Usually, or in general, it's you get slightly more friction factors in open hole and slightly less in casing, because the casing is like metal and it's usually polished when you rotate, so it gets reduced with time. But this is kind of guideline, but you have to see it yourself in the field you're drilling. And then the trajectory. So your well path is really critical, because if you drill vertical well, it's different than you drilling S-shaped well, than ERD well, or HB, deep HBHT well. So it's quite a lot of differences that may affect your outputs as well. And then you should also have your drill string. And like drill string, we mean the bit, the BHA, hip weights, drill pipes. And as we said, like the weight of drill pipe plays a role for the outputs. The stiffness of drill pipe plays a role for the outputs. But when you do this simulation, you have also to do the hydraulic simulation to make sure that you may have the best setup for torque and drag, but it might not work it might have high ECD, for example. So it might not work for other simulations. So you have to optimize all in one. And then the friction factors, which we just discussed. So you need to have, based on your scenario, so you need to choose what type of scenario you're doing. As we said, like you can be doing drilling, tripping, or reaming scenario, and then you should have the right friction factors. Like if you are, an example, you're doing a tripping scenario, you want to check your max hook load when you trip out, and you have rotation friction factors, then that doesn't really help, because the software will take the zero here in the translation friction factor. So it has to be in the right place. So you have to make sure which simulation you're doing, or which scenario you're doing, and then you have the right friction factors for it. And then the mud specs, usually the most important factor here is the mud weight, and that affects your buoyancy factor. And why it's important? Because it affects your weight or buoyant weight of your drill string. And again, at the end, it affects your tensile load. So this is the way it's related. And then the technical limits, which you have to have before you start any design. So you need to know your rig limit, hoisting system, pumps, torque, top drive torque, RPM. So you have to have all this information before you do that. And also you need to know how the formation integrity, how much ACD it can take before you get into losses. So there are a few things that you need to look at. You do the simulation at the current bit depth. You need to have like an ROB. And then the block weight is also important for your simulations. And as we said earlier, you need to have the downhole torque, for example, because it's a factor of your simulation. It will add on to your overall torque. So these, in general, these are the main inputs you need to have for your simulation. Okay, so what are the main outputs you get? Again, side forces. So you get the side forces, which can be due to tension, weight, or buckling. So this is one of the outputs you have to check every time you do drill string design, and then you have to make sure what kind of changes that you can do to improve the side forces. Another thing you can, one of the other outputs that we will discuss also in details is basically stresses. So in general, we have different types of stresses. So we have axial stresses by moving string up and down. So when you have axial movement, then you have the axial stresses, torsion stresses, which is created from rotation, and then the bending stresses, and von Mises stresses, which is a combination of all of these stresses. And then the axial loads, basically the neutral point design. In general, the recommendation was to have your neutral point in the BHA. However, in some circumstances, that doesn't happen. So you may have your neutral point in the drill. So if you drill like long ERD well, then your neutral point will be pushed back in the drill pipes, and that happens most of the time now. You need also to look at tensile load and margin of overpulls. What does that mean? So as we said, the worst case scenario for axial loads is basically tripping out. So if you have very long well with low inclination, what happens when you pull out? So you have most of your string hanging on the traveling block, and then on the hoisting system, and then you need to pull this out. So if you have very stiff, heavy string, which is close to the limits of the drill pipe, the tensile strength of the drill pipe, so it's really critical if you get an overpull. So what happens? You add more weight to your axial loads, and then you may exceed the 80% of the axial yield, which is really critical in that case, because your drill pipe might fail in that case. So it's quite important to know how much the max axial load you get at TD, and how much margin of overpull, how much can you pull more than that if you get stuck, for instance. So this is really important as well, but unfortunately we don't have time to cover all of that. And then the last one is buckling, which we will mention some of the criteria that can affect the buckling here. But basically the buckling is what we show that the string might buckle, and one of the issues with buckling is when you have sinusoidal buckling, your drill pipe might not fail, but what happens is that, like, you're doing sliding, for instance, if you're DD and you're trying to slide with motor, and when your string starts to buckle, then you have more contact forces with the formation, and that will actually reduce your surface weight on it. So you apply, let's say, more weight from surface to drill, and then you have your string getting buckling, so you have more side forces, so you lose the actual weight, and then you have weight transfer issue. So your weight doesn't go all the way to the bit, and you can't really drill further. So it's really important to make sure that you don't buckle, or you have enough room before you get your string buckled. And then torque is the rotational force, as we said. So what we get with the torque is basically you need to make sure that your rotational torque or your torque is within your drill pipe limits. And there is actually a tricky thing about it. Again, unfortunately, we'll not cover torque here, but there is a tricky thing about torque is that when you have a tapered string, so you may think that, let's say you have 500 meter of 658 on the surface, and then you have 5 inch for 4,000 meter. So you may just look at the max torque that the 658 can handle, and you think that the drilling torque is within the limits for 658, but it's too short. And then you have to actually think about the torque or the actual torque at the top of the 5 inch drill pipe. So you need to check for every component. If you change your drill pipe, you need to check the max torque or the drilling torque. You need to make sure the drilling torque is within the makeup torque, or 80% of the makeup torque of your drill pipe. Axial displacement is basically, just to make it simple, it's the pipe stretch. And how's that important is it's if you do logging runs, and then it's important for actually correlation, so you know how much stress you should expect. In general, you have the pipe tally, you think your sensor at that depth, but in reality, your sensor might be shifted because of the shift, so it might be somewhere else. So you need to know that as well. Okay. Again, just a refreshment. Side forces basically weight, tension, component buckling, and stiffness. So we'll discuss the side forces output now. And if you remember from the equation, we'll give an example about the tension in dogleg now. And as you remember, the side forces generated from tension is basically affected by the dogleg severity and the tensile load. So here are two examples. If you look at this is a well bath made 6,000 meter well, a little bit deep well, I would say. So it's almost 1900 feet. 19,000 feet. And basically, let's look at just a kickoff depth, which is 380, and then we have a dog leg of 1 at the beginning. So we have a very little dog leg, which sometimes is used here basically, and it works. So we use that at least. So this is a real example. And we have it like 1 degree dog leg at the beginning, and then the max dog leg is like 1.5. So this is a low dog leg for the kickoff. Let's see if we use the same well, and then we increase the dog leg to 3 for the kickoff, how much that would affect our side forces. So we have the two examples there. So we have 1 dog leg, low dog leg here. And if you look at, that's actually the side forces graph. So we're tripping out full, and then we're a bit at TD at 6,000 meter, almost 6,000 meter. And then you actually having the limits, as if you remember. So we have a ton every 10 meters. That's the limit, that's the recommendation. And then you have the measure depth, and that's actually the side forces. So in the middle, then basically there is no side forces. Here it's just vertical before the kickoff. And then you see there are the effect of kickoff from inclination or azimuth, which are in a way the build or drop section. And then that's the magnitude. So it doesn't look at the direction, because these two, inclination azimuth, it shows you if it's dropping or building. So if you look here, we see that the side force is almost 1, and then the magnitude on the second kickoff is almost slightly over 1. And again, everything is over 1. But then when you look, when you see these spikes here, that's actually the bit, which is you should expect 2 high side forces. It can't be avoided, and the drill core, if any. But usually when you see such a spike like this, that's a crossover. You're changing the drill pipe here. So that's basically 578, and that's or 658, and that's 578 at the bottom. So you see that in general, I would say this is actually what we want to see. So you see, you have low dog leg, you have low side forces, and then low torque and drag, and at the end you have low casing wear and drill pipe wear. So that's a way we should design our wells. Looking at just increasing the dog leg from 1 degree to 3 degrees, what happens here? So you see that was almost 1 ton per 10 meter. Now it's almost 3.7. So it's almost 4 times higher. So you see the effect. So you can imagine if you set the 13 straight inch casing, you start drilling 12 1/4 inch section and 8.5 long 8.5 with low ROB, you have a lot of circulation, and you're rotating the string for long time, which are 2 main factors that increases the casing wear. If you have such side forces with time and rotation, what happens? You will probably have a lot of casing swarf getting out to surface, and you will you might lose your integrity, well integrity, or you may have a hole in the 13 straight inch casing in that case. Okay, so that's basically the effect of the drill pipe, of the dog leg. So you can see how important is it to think about the full picture, not just to kick off. And yeah, I know sometimes it's difficult because you have the anti-collision, you need to get rid of anti-collision, and you need to make sure that you kick off, but you have to optimize. So it's a key word for everything. It's optimization. Then let's see the effect of, as we said, like it's the main factors that affect the side forces are dogleg and tensile load. And when we said tensile load, we agreed that it is the weight of the string. So let's see how the change in drill pipe size or weight would affect the side forces. So same example here with high dogleg, and basically you're trimming out. We have 658 heavy drill pipe. Again, it's quite high because it's heavy and you have more tensile load below the kickoff point. And that's the worst part, because the thing is, the idea when we discuss that not having high dogleg that shallow is that when you have the dogleg right here at 300 or 400 meter, what happens? You still have the whole string below. So if you have the dogleg here, then you have, let's say, 1,000 meter, 2,000 meter of heavy string underneath, then the tensile load is much less. But when you have the load here, when you have the dogleg here, and you have the whole string underneath, then what happens is that you have much higher tensile load, and then you have much higher side forces. So that's why you usually see the side forces are higher on the top here at the high dogleg, but it's less when you go down. And then same example, we just changed the drill pipe from 658 to 5-inch. What happens? It dropped. It's not the optimal yet because it still have high dogleg, but it's less. So these are the two main factors that affects the side forces here. Now I hope that's clear enough for side forces. Again, why do we really need to focus on side forces that much or reduce the side forces? As we said, like side forces are one of the main causes for torque and drag, and it increases if you increase side force, then you increase the torque and drag, and you might not be able even to reach a TD if you're very limited with your rig and you are at the limit of your plannings, then you might not be able to reach, because usually it's ideal on the paper on the plan, but when it comes to execution, then it's really important. So you may expect more doglegs even when you execute it. So if you have planned for 3 degrees dogleg, then you can easily see 5. Again, if you have too high side forces, then you have contact or force from the drill string into the casing, and what happens? You have this friction between them, or the side forces between the drill pipe and the casing will create a swarf from both. So basically, you have metal debris from that friction between them, and this swarf, we call it the swarf, might go to ruin your surface equipment, your downhole tools, and you may get the failure in your tools, and you trip out fall. So again, it's really important. Plus, if you have a severe casing wear, there might be a wheel integrity issue. So put that in your consideration when you do a design. As we said, also time and rotation are really critical for when you have high side forces, because if you have high side forces at that shallow and you drill a well and you have few issues, so you have to back ream or spending much time rotating down there in each section, then what happens? You have so much rotation and so much time that it may cause or might cause a failure in your casing. Okay, then the second output we'll discuss today is basically buckling. Then I'll get back to the question in the first session. So what happens is basically buckling is affected by a few things. If you look at it, so it's basically the drill pipe specs, the Young's modulus, the moment of inertia, the difference between OD and ID. So it's basically the stiffness of the drill pipe, the buoyancy factor, because it affects the weight as well of the drill string, and the weight of the drill string itself, for sure, and the inclination, which is a really important factor here, the inclination of the well, and the clearance between your drill pipe and your well bore. And your well bore walls. So if you have small drill pipe in a big size hole, so what happens is that you're more prone to get buckling. So that's a really important part in when you do the design. So you have to select the right drill pipe to avoid buckling in string. Another thing also is the inclination. So you have to think about that if you need more weight to keep your string under tension for a while. Because if you have vertical well or low inclination well, then you have more chances to get your string into buckling scenario. Okay, let's just go through a few examples here quickly. So as we said, like we have two types of buckling. We have sinusoidal buckling in orange here, and then basically it happens first. And then if you continue increasing the weight of it, then you get into helical buckling. So you have your weight, your depth, and you know what kind of weight on it you can apply without getting into buckling mode. So you can apply here, for example, you can start with 27 ton without getting any sinusoidal buckling, and then you can increase it slightly to even 30 ton at that depth. So you do that with, you have 5-inch drill pipe, everything looks okay, so no issues, and that's high inclination. And then let's assume you have lower inclination in the well, like 20 degrees less. What happens here? So you see that we started with 27, we managed to increase to 30 before we get into sinusoidal buckling, and then now we're almost 40% less. So we're about 16 ton before we get into buckling. So that's the effect of the whole inclination. So, and sometimes you can't really change that, but you can change your drill pipe. What you can do is you can add more drill collars to keep your string under tension, so you don't get into buckling that easy. So this is something you can, these are things that you can do to avoid buckling. So keeping the same scenario, what if you have 3.5 drill pipe, which is, it's not realistic in that case, but just to show you the effect of the clearance between drill pipe and the well bore, and also stiffness of drill pipe, because the 3.5 is quite flexible compared to the 5-inch, which is more rigid than the 3.5, and also the clearance is less in the 5-inch than the 3.5-inch drill pipe. So that's, you see it now was 16, now it's 8, so it's 50% less. So you get into buckling that fast, so you can't really drill the well with more than 8 ton, and then you have very slow RB, and you might not be able to drill it at all. Okay, stresses, as we said, like we have few types of stresses that the drill pipe might be subjected to, and these are axial stresses moving in and out, so axial movement. Bending stresses due to vibration or high bends or high dogleg, and torsion stresses due to rotation, and then von Mises stresses, which are basically the major thing we look at. It's a combination of all these stresses together, the three of them together, and that's what we usually care about in the string design. So the objective when you do the design is to keep the von Mises stresses below 60% of the yield strength, and that's to avoid the fatigue to the drill pipe. So you can actually drill with when you exceed 60%, but you will not be able to use this drill pipe if you trip out 4. So once you trip out 4, what you should do is basically to send it for inspection. But if you drill over 80%, which is your limit, you shouldn't actually exceed 80%, then you're not, because if you exceed the 80%, you're not allowed to use the drill pipe any further. So that's really important, because you may lose your string in hole. Just quick example on the stresses here. So you see that's basically that's the maximum or the yield stress of the drill pipe. So it's part of the drill pipe specs, and this is mainly driven by the drill pipe spec, so the grade of the drill pipe you're using. So however, here you see this line here, it indicates that we have changed the drill pipe size. So that's 658, 578, but what we have here, we still have the same grade, it's S135, and that's why it doesn't really change the property. So it's related to the grade of the drill pipe. So looking at the yield stress here is basically 100%, which we never get there, and then the 80%, which we should not exceed. And usually that's a 60%, which we try to be lower than that, but sometimes you drill very long wells, ERD wells, like 9 kilometers, and then you have to at some point at TD, when you trip out fall, then you might be, or you back ream at close to the well TD, what happens is that you might be exceeding slightly the 60%, which is fine, but then all the string or all the drill pipes that have exceeded the 60% should be sent for inspection later on. Then you have the bending stresses here. You have your torsional stresses, you have your axial stresses, and then your von Mises stresses, which is the summation or the sum of all of them. So you see that what we're doing here is basically you can tell that we're back reaming because you have the axial and the torsional. But if you have your torsional is 0, then it's actually tripping out fault. So you can actually tell by looking at the graph what kind of operation you're doing here. So we're back reaming at almost TD, which is close to here. Yeah. So if you look at von Mises stresses here, so it's almost 4,000 bars at low dogleg 1 degree. So this is the effect of dogleg on the stresses. How the stresses will be affected by, again, by high dogleg at shallow depth. Again, doing the same well bath with increasing the dogleg shallow depths to 3 degrees dogleg, which we've done already for side forces, is you see that the VN stresses has increased from 5,000 to 4,000 bars to almost 5,000 bars. And that's still safe, but imagine yourself in a different situation, and let's say you're close to TD, and then you have an obstruction that you can't really pull through. You can trip out, fall through it, and what happens is you need to back ream through. And then when you back ream, you have an overpull at the bed. So you have some obstructions at the bed that adds more stresses. And that's basically the scenario here. Like if you look at this scenario, so you have 70 ton at the bed, you need to get out of the hole by any way. And what you get here, you exceed your 80% if you are in that case. So you actually know in advance when you do the design for this well, what is the max overpull you can do or you can go for when you design the well before you get into 80% of your yield strength. So that's why it's really quite important to know ahead what is your limits and how far can you go before you get into trouble. Yeah, so that's basically it. I have covered a few things, but I didn't manage to cover everything. I hope that you found it useful and it adds some information to you. Thanks a lot. Now let's take the questions. So the first question is how such forces impact external corrosion. I'm not sure if you mean the side forces when we start creating some swarf from the casing. I think that's what you mean. To be honest, this is a kind of tricky question because I think it might add based on the mod we have in the components in the mod. So it might add to the corrosion, and it's a good point. And that's why when we do, after we drill a well and then we need to do any other operation on the well, that's why we have to look the casing and check the corrosion for it, because I think it will add some effect. It might accelerate the corrosion. Does it have any effect on the seaming job and well integrity? It depends on where do we actually create. Like if we create a hole or something, then it will add an effect, but not on the seaming job itself, but it will be on the well integrity. Seaming job might not be affected anyway. Most importantly, one thing is what we design for seaming jobs. Let me just try to talk about different things now. One of the things that we need to think about when we drill a section with an ECD, where we can check for drilling that the drill string fits for torque and drag, it fits for hydraulics and ECD, but also we have to have the mod weight, which is enough for seaming job, because when you do seaming jobs, basically we get much higher ECD. So the well can be drillable, or the section can be drillable in terms of, well, it can be achieved in terms of drilling, but again, we still have to case it and cement it. So we have also to think about that in the future. But thinking about the casing wear, I don't think it will affect the seaming job itself, but it will affect the wheel integrity if it happens. Failure models, we can part the string. So this is one of the failure models. There are so many failure models that we can discuss in details when it comes to drill string design in specific. We're looking at the drill pipe specs. But failure models is basically what I mentioned. If you see the pictures from sinusoidal buckling or helical buckling, you can't really use just drill pipes anymore. So this is a failure, or you can even get twisted. And if you exceed, let's say, if you exceed the max torque on the drill pipe, then you have a back off. So basically, you actually lose the threads of the drill pipes if you exceed the torque on it. So the thread of the drill pipes will be damaged, and you will have fishing hole. How does these forces impact measurement of depth in both logging and perforation TCP? So basically, the depth. So when you do logging or when you do, it's different than when you use drill string and the wireline logging, because both of them will show different log. But what we try to do is to try to be as accurate as possible. So we see shifts anyway between wireline logging and BHA or drill string depth. And that has to be in a way when they do the TCB. So I'm not an expert in TCB and perforations, but they have to do that again and to check the depth by themselves. Von Mises, what is the relationship between von Mises and flow rate? How is it affected? There might be very little effect. I think I don't see. Well, it's just some tiny things. If you think about the impact force, if you're pumping with high flow rate and there is an impact force at the bit that pushes the string further up, and then it reduces the weight of string a little bit. We've seen that if we try to take the weight of the string without pumping and with pumping, so we see some difference. But I would say that won't be the major contributor to the stresses in that case. But it's very tiny changes, I would say. Okay, if there is no more questions, then thanks a lot for joining. I really appreciate it, and thanks again for the organizers for the event. It was really a pleasure for me, and wish you all the best. Thank you.